Alright everyone, let's get to work. But you're watching a physics channel. Why am I telling you guys to get to work? Well, that's what I'm going to explain in this video. And no, don't worry, you're not going to have to go work in an office or do an office job. On the contrary, you'll be able to have fun learning about work and energy. And energy is something that some of us have a lot of and some of us not so much. So, let's start explaining this concept. Now, work is inherently force times distance. That's what it is. Times distance. Now, if you've already taken the physics course or you know calculus and you've done it, you might know this as the integral of force with relation to time. But this course is algebra, so not yet. It's time to keep it simple for you guys. So, what does this really mean? Well, this means that if I push a 1 kilogram object, or let's say I apply 1 Newton of force across 5 meters versus I apply 1 Newton of force across 20 meters, the one with 20 meters will take more work, of course. And that also explains why you feel so tired after you push a heavy object or something for longer, or after you're running or doing anything for longer, as moving the weight of your body or moving the weight of anything else inherently requires more work. So that's why people are way more tired after like a 5.5 hour tennis match versus a tennis match that takes like 30 minutes. So that's work. Now, when I was talking about why you're tired and stuff, some people would say, well, that's because you've run out of energy. Now, you can't really run out of energy like that, and that's different. That's for another video, which will happen in the future, I promise. But now you might have thought, oh yeah, you're running out of energy. And that's really kind of also what it is. Energy. This is the stuff that makes things happen. So energy is the stuff that makes things happen. And it comes in many, many different forms. Some of the most common of these forms will be kinetic and potential energy. So let's write these down. Now, of course, there are other types of energy and stuff, but they're much more advanced and we will not be covering them. So this kinetic energy is energy of motion. This is the energy that an object has when it's moving. Like if you have a ball, hit it off a tennis racket, that ball will have a certain amount of kinetic energy. And that's why when I want to hit the ball back on the other side, it takes energy to counteract that kinetic energy that was released off the ball when my opponent hit that ball. Now, potential energy is the energy of position. This depends on where on the earth or in the universe did this energy happen. So that energy is completely different. That energy is like if I have a ball, if I'm holding it in my hand before I'm going to toss and serve the ball in tennis, that ball will have a certain amount of potential energy because it is a certain distance above the ground or above wherever, our reference point is. So that's why potential energy is the energy of position, and that's why it takes effort to hold that ball. Because if you keep your arms straight and hold that ball for a very long time, your arms will start to hurt from fatigue. Because that you're exerting that energy to counteract the force of gravity pulling your arm and the ball downwards. So that's potential and kinetic energy. But how do we calculate this? you know what it is. Oh yeah, if I throw a ball, that's gonna happen, that's gonna have kinetic energy, and if I hold a ball, etc., etc. But how do I calculate this? How am I supposed to bring this down to a number? So this is where we get into the units for work and energy. This unit is the joule. No, not the crown jewel, not all of that, just Joule. We abbreviate it just J. Now this joule is equal to a Newton times a meter. So that's what it is. That's what a joule is. So, okay, good. We know what our units are. We know this, we know that. But again, I told you that I would teach you how to calculate this. But I only told you the unit. So, let's go to kinetic energy. Kinetic energy is calculated as 1/2 of the mass times the velocity squared. And potential energy is calculated as mass times gravity times height. So now we know what kinetic and potential energy are. And notice how potential energy sort of follows that work thing, where you have the force, where this is the force of gravity, and you have our height, which represents distance. So also, kinetic energy also follows the same work structure, but how and why comes from calculus. And that's not a physics course that I'm trying to create for you guys. I'm trying to make sure that this is more accessible to people who don't know that level of math. In the future though, I will create a calculus-based physics course for those who want to bring their skills to the next level. But for now, we're gonna stick to algebra. So what have we covered so far? We've covered what work is, what energy is, and the two main types of energy, kinetic and potential. We've also figured out what is the unit for energy and work, what's kinetic energy, and what's gravitational potential energy. If I forgot to mention that, this is the gravitational potential energy of an object not that far above Earth's surface. So, there we have it. We have everything. Except, I lied to you, we don't have everything. Who said that work is just force times distance? What if the way the object's moving and the force that's being applied on it are in different directions? Then what? Then we have to use an alternate formula, a more general formula, if you will. So the general formula for work is force times distance times the cosine of the angle between them. The reason for this is pretty simple. Let's draw a coordinate plane in this upper right corner that I'm sectioning off over here. So if we draw a coordinate plane with our force and distance. So let's have our force vector be this and our distance vector be this. Or distance, really displacement, not distance. Let's actually clarify that because, as I mentioned in kinematics, that was a very important thing, distance versus displacement. So those two are our vectors. And over here, we have our angle between those vectors. Now, if those vectors are pointing in the same direction, the maximum amount of work will be applied because we're moving the object the most when the force is in the same direction, as all of the magnitude of that force is being pushed in that one direction. But what if it was 90 degrees away from each other? What if instead of that, our distance vector looks something like this. Now that's a problem, because by our definition, there would be zero work. Because cosine of 90, first of all, is 0, and second of all, when you split the force into its components, the component of the force of the, like, if we have our x-axis be where the force is, and then our y-axis would be where the distance is, all the magnitude of that force is going in the x direction, but nothing in the y direction. No amount of magnitude of that force is being put in that y direction in order to create that distance. So work has to be 0. So there you have it, all the formulas. Except I was joking again. We're not done. We need to cover one final extremely important theorem that we will discuss more later in other videos. But the purpose of this is to introduce it to you, as this will be very important in understanding conservation of energy, the thing where it's like energy can't be created or destroyed, and it is very essential also to understanding how all these forces are caused and how all energy is really the thing that makes everything happen, like I claimed in this video. So, what is this called? This is called the work-energy theorem. Now this theorem states that the work is equal to the change in kinetic energy. Now, kinetic energy, we write this as KE. And we write the potential energy as PE, just so you know, for the future. Now, since work is the change in kinetic energy and potential energy looks a lot like work, then it looks like something has to do with kinetic energy and potential energy. Now, when something has to do with kinetic and potential energy, that becomes mechanical energy, and that will lead into conservation of energy. So, now you know what everything that you really need to cover is. The energy, work, what it all is, different formulas, and now you know a very important fundamental theorem that helps with understanding conservation of energy and why this works. Now, again, the derivation for this theorem is more calculus-based, so I will definitely cover it in the future when I go over calculus-based mechanics. So, that's sort of it. Except, no, I'm joking. Just one small thing. If you look at the formula for work, and you realize that force and displacement are both vectors, you'll realize that this is the dot product between the two. We've gone over a lot in this video, and I really hope it all makes sense to you. If you have any questions about this though, feel free to comment down below any questions or anything you have for this channel so I can improve it for all of you. But besides that, thank you so much for watching this video. It really does mean a lot to me. And if you enjoyed this or if you learned something new from this, make sure to like, subscribe, and hit that notification button for more awesome videos just like this. So, once again, thank you so much for watching this video. See you in the next one, and bye-bye.